buying a car in 1899, you would have had three major options to choose from. You could buy a steam-powered car, typically relying on gas-powered boilers. These could drive as far as you wanted. Could buy a car powered by gasoline. However, the internal combustion engines in these models required dangerous hand cranking to start and emitted loud noises and foul-smelling exhaust while driving. So your best bet was probably option number 3, a battery-powered electric vehicle. These cars were quick to start, clean and quiet to run, and if you lived somewhere with access to electricity, easy to refuel overnight. And while some models still have a high upfront cost, they reliably save their drivers money in the long run. One of the main reasons for the efficient working of present electronic vehicles is the modern Synchronous motors, which is basically an induction motor. Clearly, as you can see, the rotating part here is an arrangement of conducting bars. Alternating currents from the battery packs flow into the motor's outer windings. This will create a rotating magnetic field. The fluctuating field interacts with the rotor bars and generates electromotive forces on them. These motors are efficient, but not up to the mark. For instance, long drives at cruise speed lose 3% to 4% of energy to generate currents in the rotor bars, which is definitely not efficient for an automobile. The most crucial performance parameter is its starting torque. Even though the induction motors have a better starting torque than IC engines, there is a motor technology that provides even better starting torque from the same motor. Motor technology based an efficient permanent magnet rotor can be made by placing permanent magnets around a solid iron cylinder. These 4 permanent magnets produce a combined magnetic field. The shape of this combined field is quite important. The combined magnetic field of these 4 magnets can be plotted as shown. Now we need to analyze the interaction between the RMF and the combined magnetic field. Analyzing force interaction between two magnetic fields is simple. Just observe how the south and north poles interact with each other. For simplification, let's hide the magnetic field produced by the permanent magnets and keep only the north and south poles. The force interactions between the different poles are shown here. At this angle, the RMF definitely produces a torque on the rotor. Now let's rotate the RMF to 45 degrees. Interestingly, at this angle, the rotor experiences maximum torque because the attractive and repulsive forces are passing almost tangential to the rotor and they are producing the torques in the same direction. In this design, the rotor has no induced current, which reduces the input energy required and leads to higher efficiencies than of induction motors. A permanent magnet motor produces good torque when you start the car or ride up a hill. However, when the car cruises down the road at high speeds, permanent magnet motors have terrible performance. The villain here is the back EMF. The magnetic field lines produced by the permanent magnets link with the stator windings and generate an EMF there. This EMF is called back EMF. Moreover, these high-strength magnets also result in magnetic eddy current losses, which increases the heat in the machine. An interesting phenomenon can be observed when slots are cut in the iron. At this rotor position, the rotor is in a high reluctant state. However, if the rotor is turned by 45 degrees, it will face a very low reluctance. The rotor always has a tendency to attain a low reluctant state. Therefore, if the magnetic field rotates, the rotor will rotate along with it, so that the rotor can always be in a low reluctant state. The rotor's rotation speed will be the same as the RMF speed. The torque produced by this phenomenon is known as reluctance torque, and such motors are called synchronous reluctance motors. Syn RMS are highly efficient, and they don't have back EMF issues. In short, permanent magnet motors are good at low speeds, and Synas are quite good for high-speed operations. If we can integrate the CRM technology into the permanent magnet motor we saw earlier, such a motor could work efficiently at any speed. We can easily achieve this design integration by placing the permanent magnets into the slotted cuts of the SINRM motor. This way, even at high speeds, such motors won't produce much back EMF. Obviously, at this stage, the torque production will mostly come from the reluctance effect. The Model S cars have IPM Syn ERM fitted at the front. The IPM SYNR motor has efficiencies of up to 96%, compared to the traditional induction motors of up to 94% efficiency. Effective cooling of an induction motor's rotor is a big challenge. This issue is not present for IPM Synas. With the added advantage of reluctance, these motors have higher torque values than induction motors. IPM Synths have definitely set new stage standards in the EV world. From cars looking like this to this, electric vehicles have traveled a long way.